Okay, thanks for having us. Sorry it's late in the day. Hopefully I won't put you all to sleep. It's a slight change of emphasis. This talk is a lot about preparing, using geophysics data to prepare for 3D modelling. And I think it's an emerging discipline, or it's an old discipline, what an interpreting geophysicist would have done traditionally. But I think it's this discipline of old has to be updated, and I don't see many people doing it. I do see the need for this, so I've decided in the last year or so to put quite a bit of effort into trying to bridge the gap between what I would call traditional geophysical interpretation disciplines prior to and as an aid to helping create the 3D models. You know, so let me just, I have one practical or two practical demonstrations in real time I can do that I have snapshots of, but I'm quite happy they take about a minute each, which we can try and do as well if you actually want to see practical demonstrations. That's why I called it practical. And some of this is borrowing from a few talks. There's some new algorithms in here, so let's just kick into it. So, as I say, a discussion about traditional, what are geophysicists in interpreting their geophysical data as supposedly to help geologists. This, of course, puts a finger on a terrible problem in our industry, that the geologists and the geophysics very rarely communicate often, and often the geophysical interpretations are ignored, or the geologist wishes to interpret the colours in the geophysics images, often appallingly. So we try, I see such a huge need to actually try and move into this space to offer assistance. So in that sense, let's see how it all goes. So the traditional methods, so traditional methods in geophysics interpretation, I think, have taken a holiday. I'll just say this. Almost nothing has happened in the last 10 years in improving traditional interpretation, and it's been hijacked by inversions, which I think are of limited use. Unconstrained inversions, or what people are now calling lazy inversions, are actually a lot of times waste of time. So I'm actually going back to traditional methods, and I'm going to talk about those a little bit and how we can perhaps reset and go forward from there. And, you know, the Naudi methods and the worming methods and upward continuation, and I'm not going to get to all of these because there's so many of them, but you can, if you take the philosophical approach I'm going to talk about today, there's actually a great deal of work that can actually probably help geologists a lot in making 3D models if the work gets done. And I'm going to show you that. And of course, geostatistics and geophysics has generally not been, geophysicists haven't generally taken up the principles of geophysics. Geophysicists haven't taken the geostatistics very well. And that's another huge omission. And it's bizarre, why not? So just to recap a little bit, back in the 80s or 90s, Henri Naudi in Paris, when he worked for CGG, came up with this idea of simple models automatically coming off the TMI in this case. And of course, as an interpreting geophysicist, because of the ambiguity, ends up having to make a bit of a decision. Is it, you know, in a data set like that, is it a fold, is it a dike, or, you know, whatever. So sort of almost naturally, or by training, I suppose, in the practice, in our geophysics practice, this used to be the case, that people would have a fair idea when they look at a magnetic image and say, oh, that's the dike swarm or whatever. And then from that, you can then pick a tool and then do an interpretation. And of course, also in the early 2000s, this is quite popular still, there's still work going on in this area, but in Australia it's multi-scale edge detection, the rest of the world, but in Australia we call it worming. And the basic idea is that you have a contact with a density contrast across it, you have a profile of gravity, You upward continue that profile of simulating, observing the gravity at different heights above the body. You get a turning point. You take this first derivative or second derivative of those at the different upward continuation. You get the turning points, the zero curvature points, and you can construct, you can pick up where the edges are. That's why we call it multi-scale edge detection. And so traditionally, like 10 years ago, this type of work was established, and Mark has been involved with it. Everyone in the room has been exposed to worming in Australia. It's very popular, well known. So, and also well known from 10 years ago that when you get the splays like this, oh, that's because the body is not vertical and the contacts are dipping, and this knowledge has been known for a long time. But stuck in 2D land, stuck. And a current example of doing it on the isostatic gravity correction map of Australia, the GA1, you can get thousands of linears, and there's all different ways of cutting and slicing a 2D geophysical technique, the worming technique being applied to gravity. So that's a quick run through some of the things that we have in our toolboxes. So what are the barriers for sort of putting a bomb under geophysics and trying to make it move into 3D space? What are the barriers? So, of course, the classic one is that there's the ambiguity of potential field interpolation. That's a biggie. And some of that's due to the fact of the quality of the actual measurements. And in the last 10 years, there's a transition. There's a fantastic transition going on to gradiometry, to vector work. We're moving, there's a profound shift in instrumentation going on as we speak. And some of the software tools and the methods and the ability of the training isn't keeping up. There's a lot of new things that become available if we use our brains. So, of course, a lot of the data sets that are collected are badly aliased and not enough emphasis. There's almost no emphasis by geophysicists on trying to extract foliation information from the geophysics data. That's more or less, I'll come back to that. And then I was talking before about, the simplistic codes like tilt angle. In particular, I'm quite ambivalent about the overuse of tilt angle by the uninitiated to extract too much information, seeing too much into it without understanding the limitations of some of these simple methods, etc. Anyway, so we know there are barriers and blockers. That's just a couple of them. What are the innovations that are available for us to pick up and embrace and try and make use of if we're creating new software tools or techniques? And of course, in this forum, everyone knows about co-Krieging or implicit functions. Implicit functions are well overdue to be embraced wholeheartedly in geophysics. They're missing from geophysics. The ability to create 3D surfaces directly from geophysics data sets is well overdue. It's a set piece. We know how to do implicit functions. They're missing from geophysics largely. Why? And of course, there's plenty of nice algorithmic stuff that's around with triangles and tetrahedrals and I guess in the last 10 years there's been what I call the rise of the computational geometry engines. And I like to talk about VTK and Seagull, and there's plenty of them around. So the ability to actually deal with complex geometry in a rational manner, bridging between geology and geophysics, is no longer, it's a challenge, but it's doable. Okay, I'll just keep going. So for instance, here we have this is actually derived from magnetic tensor data in South Africa. Probably shouldn't be showing it, Mike, but no one else knows, except you and me. But topography and the dike, and we're showing an adaptive triangulative mesh. So with geophysics, it's possible to have the high resolution information where you have it near the surface and adapt and sort of thin out the triangles And that seems like a pretty rational thing to do with our Dike modelling. And you can have it as the full volume, or you can have it as skeletonized with a thickness attribute for each triangle. That's the sort of thing we would like to see a lot more of. So let's go to the core of how the hell do we get things moving. And I think the core is to actually go after orientation data out of the geophysics and actually try and make it defendable and rational, and at least we can have a good discussion. You mightn't like it, you might disagree with me, but let's at least start to have the conversation about how you do it. So I do like to put this one up. This is a philosophical point, I can skip it, but I do like to have a little rattle on about this. When you do have it, what do you see in a geology, in a gravity, correctly, as far as we can tell from the best geophysics practice, when you actually reduce the observed gravity data to an isostatically balanced and the basins are properly compensated, what's left in the signal? And basically you're going to see, what you're going to be seeing is the edge effects. It's dominated. The signal should be dominated by the edge effects. And the bulk mass differences, by definition, that's what an isostatic balance is. It's actually minimising the bulk mass effects. So therefore, that's what we start with. And if you actually have the joy of measuring the gradients rather than calculating the gradients, they're going to be much better at revealing the subtle detail. So therefore, by that line of thinking, it should be natural then to emphasise the possibility of deriving a 3D fault network as a primary input for geologists, if we can do it. And the missing element, dips. So how to establish dips? And boundary is hidden, dips are difficult. This is a bit about, we all know about why dips are difficult. If you're going to use gravity, the most important thing is it's only going to pick up, you're only going to be able to estimate a dip from gravity if across the contact you've actually got a density contrast. So you're only going to be able to do this on maybe 20% of faults or 30% or something like that. You've got to have a decent density contrast across the fault. This is one of Mark's, probably. I can't remember who I could credit for this particular image, but it certainly dates from the 2000 bit of work. And just to revisit back to worming, you have the vertical contact. As you upward continue the surface, you get the vertical, and as you have a sloping contact, either reverse or not, you get the step out that what I was showing you before, the splays, the worm splay. So it does reflect the dip. So we're just picking up where that left off. Now it happens that in 1992, in the Geological Survey of Canada, right next to where Eric de Kemp now works, there was a worker there called McGrath who also tackled this problem, and he published this algorithm at that time in geophysics. And it goes along this line. So as you upward continue your profile of gravity data, the toe of or the hot spot of what's being measured by the gravity it moves. So just watch what happens there. Just watch that spot there. So as you upward continue, you get that step out. So the step out and where the anomaly high is follows down the slope. And the physics has been known since 1992. So I'm actually surprised this was missed when worming was done in 2000. This connection between the physics and this earlier work was missed. So the algorithm's been around for a long while. It has never been automated before. We picked it up last year and automated it. And it goes along these lines. You have a little model like that with the dip, and you've got the depth below, and you've got the density contrast. You have a little simple thing like that. I think I'll skip a lot of the words because it's fairly obvious. And then he published this nomogram where he has you upward continue it's normalised by the thickness of the fault. You can get a hot spot, and the most sensitive part of the ability to measure the dip or estimate the dip occurs at those sort of dimensions. So this is for classic standard scalar gravity. Great, we've got an implementation. So that's the theory. Let's just see where that goes. Now before I I'll come back to that and show you that working on a calibration of the Darling fault in a minute. Just before that, while we're doing theory, I'm going to jump straight to tensor gravity gradiometry and cover the same sort of territory. So tensors, you can't ignore the right-hand rule. As soon as you go to tensors, that's what's different. So when you have vertical gravity, it's simple. You can get away with sloppy scalar thinking. As soon as you go to tensor gravity gradiometry, you have a right-hand rule, but you're still using much the same sort of model. Dips and this type of thing. And guess what? There's a little formula down there where you've got and we define something called the co-dip, but it's not that different. So we take an improved version of the thin plate, semi-infinite inflate model code this time and do the same sort of model studies. And we find that instead of not only the vertical component of gravity being important, there is also the horizontal at this angle there. So if you actually have two usable components of the measurement which directly tell you a lot about the fault. That's the big difference between ordinary gravity, vertical gravity, and gravity gradiometry. You have one extra usable measure, and of course, I'll say it may not be obvious to everyone in the room, going into the page, the GYY directly in, should be around 0 if it's a 2D body. So you have the three constraints. So given that, and sort of thinking about upward continuing like we used to do for traditional gravity when we're doing worming, let's try the same ideas. What are the families of curves you get as you upward continue? There's your step out. Like we were seeing in the traditional scale of gravity, you see that step out with dip, and you get this other component not doing that much with upward continuing. But magically, and this took a while for us to hit, there turns out to be an elliptical relationship between the xz, the vertical component of gravity, going across, right angles right across the fault, and the horizontal gradient going across the fault. And this is the theory, and this is a wonderful starting point for a poor man's inversion algorithm to directly deduce the dip of the faults when you have gravity gradiometry. And they're the components again. Just there's a sort of there's a trend line with a sort of a deviation as you go directly over the fault, and that's there as well. And it looks like we don't need to do upward continuation to actually extract the dip information from the data. Great. So how does it all start to pan out? It turns out that this angle here is what we call the co-dip, and the actual dip that's predicted is more or less, one's the complement of the other, no big deal. And then the actual dimensions of the axes are also, there's 5 parameters we can invert. One of them is the dip. And I'm not going to bore you with a lot of this, but we actually, this is plotting the same information in an Argand diagram with the imaginary complex plane there and the real plane there. And there's a whole family of curve matching which we've experimented with, and how robust the methods are to the true value, and if you've got a mistake with the density, what happens, and all this sort of thing. There's all sorts of test work going on behind the scenes here. And it turns out there's these long-term slope averages which are characteristic of the model space when we're actually verifying how robust the algorithm is to not only to getting the dip, but also the thickness of the fault and the density contrast. There are 5 properties we can get. So this looks like a nice piece of theory, and so we then go out and actually see if it actually works in practice. This is another part of our test work where it turns out if you've got exactly the right density contrast, your theoretical curves are straight lines, and if they're out at all, you get all these crazy responses as you go up and down your measured observations. Okay, so we've got two dip calculation strategies that I've shown in detail there. I'm going to skip the Naudi one because that's actually well known. I might show you that later. Now we're going to try calibrating these techniques against known, quite well-known situations. The first one is the Darling Fault, just not far from here. And there are, of course, seismic lines. This is the old New Norcia line, which is, I think it must be there. This is pretty crappy old seismic data. And there's new stuff as well. This has been interpreted and written up, and that's more or less the zone there, so great. And the other one that's up to the north, which was part of the UGA line that went up that part of that far up the coast. And you've got this main feature there where you get the main gravity high. These other interpreted faults, it's very difficult to see very much at all in the gravity expression there. But this is a model that was published by GA of this particular, where the seismic line cuts along there. So taking our upward continuation, the traditional upward continuation of the gravity of Australia, and taking the total horizontal gradient of it, just spelling it out, you get these, the Darling Fault has an enormously strong signal. It's very easy to find it. It's not very hard to find. It's one of the only features that can be seen from satellite gravity features clearly. It's that good a fault, or that good a feature. So I can show you this in real time, this particular demonstration, going from the whole gravity map of Australia, subsetting, and then just picking out the worms like this, and then, of course, flipping it upside down and using implicit modelling software to actually propose a 3D fault structure. And there's a little normal vector there, and there's a few other little tweaks we've got built into the system, and that's implemented using implicit functions in the VTK type standard geometry algorithm. Something about the errors and the repeatability now. Geophysics can not only give you an answer, but when we're going to do this sort of a stunt, we can probably also start to tell you a lot more about error margins. So with the McGrath algorithm, which is the simple scalar one I'm demonstrating here with the Darling Fault, you get a density, you get an offset. This is in kilometres. Everything's in kilometres the way that the thing was done, and you get an error term, you get a correlation term, and you get the different continuation, and here you get your dip estimates at that particular point. So you see there's a mean plus a sort of a standard deviation that is sort of sitting there. So that's my summary discussion of the scalar gravity piece of work. I'm now going to jump onto the calibration of the Tensor algorithm. And the data set that's been chosen is from Nevada in the Carlin Trench. It was used for Bell geospace fluid in 95. It's written up, the data set's more or less available. So all of this work that I'm giving, I'm choosing data sets which are more or less in the public domain, and the technology can be tried yourself and do it yourself and try and figure out how I did it if you wish, no problems. And I'll give you the papers, very happy. Go for it, knock yourselves out. And in this case we're using the Tensor, what I call a Tensor grid. So we're having the full tensor gradiometry data as a grid, and I'm choosing to show an enhancement, an image enhancement of the tensor gravity using what we call the phase. So it's a phase enhancement. So it's actually a property of the rotational. So the idea is to do an AG, what do we call as an equivalent in traditional speak, an automatic gain control, an AGC enhancement. So you're just suppressing the amplitude and wanting to see what the rotations are doing. And the reason I've picked that is because it really does show you where the damn contact is. You know, it's just sitting there like beautifully. Yeah, in this particular case, you have a family of south northwest, and then you have the cross faulting there. So I picked out that particular region there for calibration, and the reason for that will come clear later on. It comes clear straight away, actually. And this is probably one of the most complicated images I'm showing today, so let me just quietly go through and discuss it for you. The first thing I've done in the white is show traditional worming, but this time applied to tensor data. But it's exactly the same idea, except, you know, the total horizontal gradient upward continued of the XZ and the YZ, and then drawing them up as contours and making the worms. So that's the worming treatment of that data set. That's the first layer. So that's that point there. The second, all the colours and the little strike vectors, so each one of those, there's little bars there, they're strike vectors. Now they're coming from a solution of the full tensor eigen solution, where I'm saying I'm wanting to find those parts of the measured gravity gradiometry where the signal is 2D. It's 2D. And let's see the strike, let's see the amplitudes, let's see it. And it turns out that particular test area, there's a very large area, not only where the contact is, but either side where there's no interfering bodies. It's just 2D in nature. It's clearly 2D. So it's a nice place to go calibrate your new technique. Okay? So this is an empirical finding. It appears as though you need about a couple of 100 metres either side of the feature for this algorithm to work so you can form the ellipse. So let's just have a look at that. Pick that area, put a profile at right angles to the measured strike, and I pick out one of the attempts. So along that profile, starting at minus 200 metres, going to plus 400 metres, we calculate, we rotate the measured tensor into the local profile coordinate system of XX and XZ. We pick out there the first two. We do a lot of other things, but let's just keep it as simple as I can for you. Just concentrate on those two columns. We do lots of other stuff. Let's poke those two columns of numbers into a best fit ellipse fitting curve. This is now real data, it's not theory, and you get a jolly good fit. So, okay, here's the first time that's ever been done where you take real observed gravity gradiometry and go after this ellipse. The theory tells us it's possible. We actually want a case to prove that you can actually do this with gradiometry data. And here it is. That's the first time that's been done. So I was overjoyed to actually see not only do the observations of XZ and XX, when they're plotted, form, you know, beautifully, but the standard sort of best fit. So if you want to know about this algorithm, just Google best fit, and bingo, this algorithm is available in the public domain. And there are the 5 things you're solving for: the centre, the axes, and the rotation. Great. So that works. Now how consistent is this algorithm as you walk along? So you don't have to do it once. You can sort of sample the fault, how many, you know, in that sweet zone, how many times. It turns out I sampled it 6 times every 100 metres or a couple of 100 metres moving along the fault in that zone, and you get pretty much the same result. Sure, there's variability, there's a strike, and something there that we didn't expect is a tilt angle. So I'm not going to talk about that today, but privately I'm very happy to talk about the tilt angle, not only the dip, but the tilt. That's quite a curious thing to be coming out of this work. We're talking about a tilt, the fault tilt, not only the dip. It's all in the tensor data. It's there. It's certainly something to talk about. So that's a sort of a summary of the calibration work. So let's dive back to traditional gravity for a minute, and we won't talk about the benefits of 3D. I think that's all pretty obvious in this forum. And how do we go from this using worming and dip calculations to creating a 3D surface? So you have to do, there's an important clustering step, and I'm not going to read all this, I'm just saying there's a clustering step, and this is how we do it. You estimate the foliation, and then in forming the clusters you've got to chop and match and all sorts of stuff. Estimate the shallowest contacts, estimate the dip, classify, and then of course we go into the classic interpolation methods, implicit functions. You've got dips, you've got contacts, so we can estimate the fault using implicit surfaces. This is by the work we're doing here. This is actually the old hat part of the whole process. Actually, this is the easy part, doing implicit surfaces. The other stuff is new. This is not new for us. So you create the new feature, assign this is finishing it off, starting to use the fault network in your 3D model. I'll skip all that, and then of course you get the surfaces, standard stuff. I'm not going to talk about that. So that's more or less the methodology. So let's have a couple of looks at case studies. Let's go back to Australia, and the worming. Now the Intrepid worming tool, I'll say it, has this capability now in version 6, not all released. We tried it again last week with PGW, and he got 1,000 faults, and it took an hour, and they're all 3D. Now that starts to absolutely send a standard laptop, spazzo, because you hit swap space at that time. That's a lot of work going on, but it can be done. It works fine on mine, but I've got SSD disks. When you have an ordinary disk, we start with 8 gigs of swap memory, no worries. But we are doing quite a bit of work there, but blow me down, you can do that. You can get a candidate. I'm not saying you're going to want to use all those faults, but here is a prior step to doing crustal studies for Australia. Wouldn't you love to have a candidate 1,000 fault surfaces ready to go? And then you can argue, and then every one of them will have the dip calculation report and have all this error estimates all done for you as sort of out of the box. It's just there, ready to go. So just to prove it's 3D, I flip it upside down and then do a side view coming back from Tasmania, looking under it, so you can see the 3D surface and the worms sitting above. So all of that is available. I won't do that demo live. I can do this demo live, but it takes a little longer, just doing the whole of the Northern Territory. But perhaps if we do want to see this one live, I can show the Darling fault calibration. That only takes a minute to do, to redo. So we're just zooming into a little part of somewhere near west of Alice Springs, picking out one of the faults, probably that one, as I recall, showing you the contacts, showing the dip, the foliation estimation there, showing the surface, showing the other ones in their companion. We create a limited box around it. You can see the worms floating above that. And it's at least something we can argue about at the very least. So that's just an example of this technology in play. I'll escape that one. Now, this one I would like to show you live. It's back to Naudi. It's a little soptomagnetics. It's the Ebagula. It's a standard training data set, very small. Likewise, this takes a minute to go from the original flight line data to this full 3D dike model. And likewise, what we're aiming to do is be able to produce 1,000 dikes for you, not one dike. And have you got any idea how hard it is? Well, you will. You're in this room, every one of you who's had a crack at doing 3D modelling ought to know a lot about how hard it is to do dikes. So if there's some way that we can give you a leg up to doing dike swarms in a systematic, simple way that gets you started, that is going to be a great boon. And this is what we're proposing. While I'm only showing you 3 or 4 dikes here, I'll do that in a minute for you. but I can believe me, we can likewise do 1,000 dikes for you if that's what you believe you're seeing in the magnetic data, and that's what you want. Here's another one we did last week from Canada, for those that have a Canadian interest. This was an ex-strata project that Glencore have walked away from, the Bathurst mining camp. Likewise, nice, very curvy geology, quite a challenge to model in 3D. We're starting on that at the moment. And we have the joy of having an FTG data set for it, likewise more or less in the public domain. So what I've done there just for fun is to see that picture there, that feature there. You can see I'm showing the total horizontal gradient enhancement of the tensor data as an image this time. You can sort of see. I'm doing that because I'm trying to show the correlation between the gravity, what the gravity is doing and what the geology map is doing in that case. The next two maps here is the phase enhancement, and this is a lot messier than the Montezuma one I showed you before. The calibration exercise I was showing, I wanted it to be so clear and unambiguous as for calibration purposes. Once you know the thing works, then you try it on more crazy situations, and this is a more crazy situation. And that's the eigenvalue plotting technique I was showing a minute ago. So that's more or less my set talk, minus the 1 minute for the live demo, if I may. And this is a fully geolocated with QC reports for every feature. That's what a geophysicist should provide to a geologist, to give him something to at least have some ideas to hang his hat on. And I think the thing that, when I presented these ideas at the forum at KEGS earlier this year, I got quite a lot of pushback from the modellers in the audience. They say, oh, no, you don't work at the data set stage, you've got to work on the model. And I actually think that's not wrong. It's wrong. You know, there's a mindset that seems to be evolving where you don't bother with interpreting the geophysics, you only ever work on models. I think there's a legitimate phase that remains in our business where you're doing interpretations on data sets. And I'm actually trying to make a contribution to that. I only raised the point because it was amazing how the audience of people, some of them similar to your backgrounds, were pushing back about the idea that you might want to still continue to interpret geophysic data sets rather than going straight to a 3D model. Just a discussion point, that's all. So I'm saying we're making a contribution to a primary referential data set. It's independent of any modelling, it's independent of scale. What do you want to store in your database? Picking up with what Gabby was saying, here you are producing primary referential data and you don't know what the model's going to be. This is sort of independent or can be done independent of what the modelling idea is. How to store, do you want to put it on the web? All the usual dilemmas come up. And I'll put one more plug in for gradiometry. It's miles better than traditional gravity. I say it's 5 times better. That's my estimation. I don't know, you're going to ask me how I come to say that. Well, it's resolving power, or you can have arguments about spectral content and all sorts of things. So I think it's better just to say it's 5 times better. And it's possible to adapt gradiometry to the traditional thinking that we've had in the past. It just needs to be clever about why we're doing it, and that's what and therefore dip becomes possible to extract. And of course, here I am starting to rev up about the use of implicit modelling in geophysics. So of course you can go after faults, dikes and sills. So if any of you are aware of the PhD that Roger Clifton is currently writing about the Northern Territory basalt that covers 40% of under the 1st kilometre deep, I believe the correct way to display that information is starting to use these sorts of ideas of implicit and getting surfaces and uncertainties, not with bloody movies and MPEGs, which is what he's gone. So having this tussle with him about how to take his ideas, which are very good, but perhaps engineer them into the 3D space to make it more accessible, more easily accessible. I think it fits into this family of thinking that we're having here. So that's another progressive thought. which you don't have to believe me or don't have to agree with, but it's something to discuss. And it's possible to get an order of magnitude more dikes and faults than you've ever thought you wanted to deal with out of this technique. Okay. That's it, guys, except for the little doodad. And I can perhaps take the first, if you're going to ask me a question, I'll run the demo while the questions are coming. So this is just a sort of, it's all batch scripts. Don't worry about this. This is how we test and develop this stuff. We run it in batch and then suddenly the 3D will pop up in a minute.
When you produce thousands of fault dikes or sills,
yeah, these sorts of things, yeah.
What's, from your calibration and QC attempts, what's the best parameter that you use to filter out the spurious ones? No, that's right. And in fact, we want to give a goodness value to every feature, and it's user tunable. What I'm not telling you are all the damn tuning parameters, you know, the lengths and the thicknesses and the susceptibility ranges or the minimum, the curviness. Believe it or not, I'm coming up with ideas that we can pick out the ring dikes sort of systematically, or the, you know, the granites. You call them ring dike, but they're actually, you know, there's a project that Peter Pekovic was working on recently where he wanted to get all the granites from Australia in a systematic way for geothermal prospectivity mapping or something like that. So can we use these ideas and these tools to help do those jobs? We can, by going for the worms which are circular or near circular rather than the long linear ones. So that's a tuning parameter. So I think it's incumbent on the tool makers and the geophysicists to not give you the answer, but to give you some parameters where you can test things and try things, but also report errors and stuff like that. Because more often than not, they're there. In this particular case, for instance, with the Naudi, we've done a poor man's, it's a formal inversion, just like it's directly what is used in Potent, if you've ever used Potent. It's exactly the same algorithm for the inversion, not only get the dike, but also invert the fit of each one of those features progressively under each flight line. That's the topography, the magnetic, it's not a very good magnetic line map, but that's what it is. It's only a grayscale, it's pretty hopeless. I didn't get the time to convert it over to pseudo-colour. And you've got your 3D feature, and the dikes are cut off by the topography for you, and you're getting your observations of the hotspots, estimates up and down each, clustered up and down each flight line to say where you think the dike is. You know, this is all dependent on the fact that you're prepared to say it's a dike. You still have to make that jump because it's at TMI. If you've got the gradient, you don't even get to make that choice. The gradient data will refuse to give you a solution if it's not a bloody dike. It won't even give you a fault if it's not what you say it is. Whereas the old potential field data that we mostly use, you can say what you like. You can interpret it. That's the ambiguity problem. That's it, guys. Anyone else? Another?
How are you getting those surfaces that you explained?
Yep. Well, that's implicit functions, right? So I did actually do it. I won't do it again. I'll go back to those slides. So you've got the Naudi method, you anomaly match. There's a TMI anomaly. You've estimated at every one of those flight lines, and I've culled them out. You mightn't look like it now. And I've estimated the location, the thickness, the susceptibility. I've inverted it locally for the fit, goodness of fit, and I've kept the good solutions, and I've clustered them up together. And then I've said, well, okay, that's a body. I've got an extent box around it, and then I've thrown that straight into the implicit function interpolator. And said, righto, it's a dike, so it's got a thickness, variable thickness, and it's got a variable, plunge, dip, etc., and the susceptibility. So you've got all that information. You've got susceptibility distribution, you've got a goodness distribution, you've got a dip, and we've made it concrete by saying, hey, here's a 3D surface in triangulated VTP shape or in GeoModeler or wherever you want it as a starting
dike. And we can not only do it once, once you do this sort of stuff, you can do it thousands of times, once you know it's starting to work. This is a demonstration of it working for dikes as part of the Naudi, as part of augmenting the Naudi thinking. And I've shown it for using for faults as part of augmenting the worming thinking. I'm proposing using it for sills, augmenting the spectre. Well, we've actually got two strategies. One of them for spectrogrant, which is Roger Clifton's ideas, but it turns out Stefan Maus from the Denver National Geophysics has done a lot of work on variography, which looks very promising, looks a lot more promising than spectrogrant. So we're well down the road of also taking his work up and commercialising that. Okay? Sorry.